Hello everyone again and welcome to my channel. In here we're going to be looking at the cationic way of actually understanding how electrocyclic reactions actually takes place. Now, to generate a cation we need to take note of two things. Why are we generating cation, and also what is being used to actually generate a cation? More specifically, you do know from your second year of university or first year of undergrad that acids are really good way to actually generate a cation on our specific target reagent, which is what we have over here. Once we're able to introduce a reasonable strong base, we can be able to protonate our compound here. So how does that actually take place? Now, we do have our ketone here with our R group, which is actually the segment, this segment and that segment here. Once you introduce an acid, this oxygen actually picks up the proton, and what we have is an intermediate where our oxygen has a positive charge, and these are R group present in there. We actually be influenced by this carbon where we have the double bond forming a lone pair on the oxygen, and what we generate then is a movement of charge going from the oxygen over to the carbon to form a carbocation on the carbon of our compound. Now take note that since this is our R group, our next goal is to be able to look at the reason why the cation is actually generated. The reason why is because we're trying to introduce an empty p orbital, so I will be able to actually have 5 p orbitals with 4 electrons in them. And while we're using that case, the reason why is because we need to be able to then subject those particular electrons to either thermal processes or photochemical processes in our way to move our reaction in one direction, where we have our protons moving in the same or same positions or in the transpositions here. So looking at the MO of our overall compound, we do have our p orbitals positioned in here, and then we have our other p orbitals in here with respect to the other structure of our compound. So let's move ahead by actually looking at how these 4 electrons are distributed in our MO sequences over here. Now the MO ways that are actually present are 5, because we have 5 p orbitals, and those 5 p orbitals has different combinations that are actually determining the positions of our electrons either in a photochemical or thermal process. Now first off, let's look at the first one. The first case, we do have 5 p orbitals that are all in phase with respect to each other. Then the second one here, we have one that is orthogonal to the other 4, where this is in phase and that is out of phase with respect to the other side, but this is in phase with respect to that. Number 3, we look at increase in number of nodes, where we have our p orbital here and our p orbital present here, which are 5 p orbitals, but then we have 2 nodes, one here and one there, and what we have is if these are in phase, but this one will be out of phase with respect to that, and this will be out of phase with respect to that, and in phase with respect to that. Number 4 we look at is, now we're going to introduce 3 combinations where we have a node here which is orthogonal, and we have 3 nodes, and that is positioned here, and the other one is positioned here, out of phase with respect to that, out of phase with respect to that, out of phase with respect to that. And our last combination is all p orbitals present, and they are all out of phase with respect to each other, where we have 4 nodes, 1 2 3 4, out of phase with respect to that, out of phase here with respect to that, out of phase, and out of phase. Now we're going to be looking at number 2 and number 3. Why Reason is because number 2 and number 3, they are going to have distribution of electrons with respect to the conditions. Now, if you look at it in a thermal process, our thermal process actually tells us that, oh, if you put it under normal conditions in the presence of heat, what we have is that we have all our electrons being paired. So this will become our HOMO for our thermal process, and this will actually perform an interesting rotational bond which leads to the formation of our sigma bond, where this will actually move in that direction and this other bond will move in the same direction, thereby causing a contradictory process that leads to the formation of our bond in an antifacial sense. On the other side, we have is our SOMO when you subject these to photons, where if these are paired, this one will actually be excited to a higher energy, and what we have is that in the presence of a photon, our number 3 will be our combination that will be used. And take note that the rotation of our bond in this case will be in a dissociatory process where there will be a superficial overlap to form our sigma bond. So this will be a disrotatory, and while on the other case it is a contradictory. Now, how does this apply to our initial question? Where is the photon here? Photon is in here, thereby this is actually a dissociatory process that leads to the formation of our compound, where the protons are actually positioned in the syn case, and while on the other side we do have our conrotatory, where our protons are actually positioned in the trans sense over there. So that's about it for our MOs that actually determine the positioning of our protons as the bonds are being rotated. And now let's look at the mechanism behind how this actually plays out in terms of the movement of protons from the acid to the target compound, and from target compound going in one direction or to the other direction. Pretty much similar in terms of dissociatory processes and correlatory processes with respect to the photon and the thermal state. So let's look at the correlatory sense. For our correlatory, what we do have is our compound, which is actually protonated here, and we have the other segment of our compound with our pi electrons. And what happens is that we have the rotation or electrocyclic process where we form our sigma bond here, and our protons actually are positioned in the trans direction or transposition due to our bond being rotated in a conrotatory sense. And what we have is our intermediate, where we have our positive charge here, and we have our oxygen and hydrogen there, and we have our other segment where our hydrogen here is actually in the trans state with respect to the other hydrogen, and what we have is our double bond formed here. Take note that the double bond which actually sees a proton, we actually deprotonate the proton from the oxygen to form a proton on this carbon. And take note that this can actually be 50-50, where one can be forward or the proton can be at the backward, because this will actually form a planar surface doing the process of proton transfer from here to there. So on the other side, we do have our bond here between the oxygen and the hydrogen that was there, but then it becomes a lone pair, and then to a double bond between the carbon and this oxygen. So what we have is another intermediate where we have the formation of our carboxyl here, and on the other side we do have our proton, which could either be front or back, represented by this wiggle symbol. And in here we have our proton that is in a trans position with respect to the other proton, and we have our positive charge here with a proton here as usual. But now, since we used an acid initially, but now the acid now forms a conjugate base, the conjugate base comes back here and actually deprotonate this proton here, deprotonate the species here, and then what we have is the formation of a double bond in here, and this positive charge disappears, and what we get is our target compound or product. We have a proton here, and we have another proton here, and this is the formation of a cyclopentanone that is a part of the overall compound, and we have our hydrogen positioned in there. So that's about it for the first part, and for the second part is pretty much the same way in terms of the dissociatory process, but take note that for our dissociatory process we have the positioning of our protons to be in the other way, where we have the protons being in the same direction. So what we do have is our compound that is an enolate or enol, and what we have here is the bond moving in a dissociatory sense. And take note that we do have a double bond initially here, and once we form our sigma bond, what we have as a result is our intermediate, the same position of our protons, and this is then reformed. But take note that in here we have a positive charge in this particular position, and we have an oxygen and a OH over there. And what we do have next is the formation of our product when a conjugate base actually comes in, and our product kind of similar a little bit to our original or our previous product that we have, which is over here, but the only difference is the positioning of our protons. These in the same either front or at the back. However, this other part here we do have our protons actually positioned in a same direction. So that's about it for this particular video. Thanks for following me through it. Truly appreciate it. Hope you're able to understand this and how the relationship of the MOs determines the positioning of our protons, either in terms of the dissociatory sense or in a correlatory sense, and how this actually is influenced by just generating a cation on a particular compound. Thanks for following me through this. Truly appreciate it. Support the channel whatever ways that is possible. Really appreciate everything you guys have done, and see you all on my next video. Be smart and see you next time.